3b is about PDFs and CDFs. PDF stands for probability density function. CDF stands for cumulative distribution function. They're different not just because of what the D stands for, but also in their role. A PDF, you're never really interested in how high it is. You're never really interested in substituting into it to find a coordinate. What you're interested in is the areas underneath them. Okay? A cumulative distribution function you do substitute into. The whole point of this is to substitute it into it. Now when you work out an area under a PDF, that gives you a probability. When you substitute into a CDF, that gives you a probability. Okay? Now let's talk about the look. The look of a PDF is some algebra and some instructions about when the algebra applies. And then other than that, it's 0. So you always see this last line 0 otherwise. The look of a CDF has some algebra and some instructions about when that applies. But its look is different. It always kicks off with a 0 and it always ends with a 1. So beyond the kick, the algebra applies between 0 and 2. When the algebra kicks out at 2, the number 1 kicks in, and before the algebra kicks in at 0, the value of the function is so if x is less than 0. Now because we are supposed to be substituting into this, we should be quite careful about when these things apply. So why don't I delete those, just so you're clear which one to substitute into. It doesn't particularly matter, I'm just trying to be good. Now, also about the look, a probability density function almost always has a lowercase f. A cumulative distribution function always has a capital F. Now, it's a classic question that you have to get given one of these and turn it into one of those, or you get given one of those and turn it into one of those. Well, step 1 is build the look. Okay, so if you have a probability density function, transfer the algebra down there, transfer the 0 up there, and create a 1 in the bottom row. Okay. If you have one of these, just transfer the algebra to the top, move a 0 down to the bottom, write the other word otherwise there, and then delete this business. Okay. Now, so that's step 1 is building the look. Step 2 is get the algebra. If you have a CDF and you want a PDF, you differentiate. So that's from CDF to PDF. You differentiate. If you want to have a PDF and get to a CDF, you have to integrate. Okay? Which means that converting a PDF to a CDF is more complicated because whenever you integrate you get this plus C business, something which is very important not to forget. Okay, now I'll tell you how to deal with that in a second. Okay, so let's do an example of a conversion in a second, but I should just point out to you that when I said that the whole point of a CDF was to substitute into it to get probabilities, it's very important that you understand that when you do substitute it into it to get probabilities, you always get a to the left of figure. So in other words, when I sub in the number 2 into this rule, I'm always going to get a probability to the left of 2. Okay, now remember, it doesn't matter whether you put a little bar on that because these are continuous functions, which means the extra amount of probability you get from including the answer, the possibility 2, is infinitely small anyway, so it never makes any difference. What I'm telling you is that these 2 questions have the same answer for a genuinely continuous distribution. Okay? So don't forget that substituting into the CDF only gives you probability questions of that kind. Anything else you have to adapt by subtracting from 1 and so on. Okay, so I'll give you an example now of a conversion. Okay, so just do an example from the book. Okay, so here is a PDF. Okay, and I need to build a CDF. So here I am writing the look. Always has a 0 at the top. Always has a 1 at the bottom. Got to have some algebras in between. I'll decide what they are in a second, but I'm dead sure when they apply. The first algebra applies between 1 and 2 because that's when that algebra did. The second algebra applies between 2 and 4 simply because that's when that algebra did. Which means it's going to be 0 to the left of 1 and it's going to be 1 to the right of 4. In other words, when this algebra kicks out at 4, this value of 1 kicks in. When this, before this algebra kicks in at 1, this value of 0 is applying. Now, how do I get these 2 algebras? Just integrate these. So if I integrate a fifth, I get a fifth x plus c. Now if I integrate a fifth x minus 1, I get, it's a bit of mathematics here, half x squared minus x plus d. Okay? Now we want this to be user friendly. We want to be able to use it to work out probabilities. So I really need to decide what these c and d's are. Now to decide what the c and d are, it's very important that you understand that a CDF, because it works out probabilities, must always rise or be flat. Okay, in other words, the graph of a CDF always looks like this: 0, 0, 0, 0, then rising, maybe flat sometimes, then rising, and then eventually it has to get to a height of 1 at which it stays. Now it also needs to be continuous. It cannot have little gaps. This cannot be the case for a CDF. You cannot have these little jumps. Okay? Now that enables you to decide what the C and the D are. Basically, if this graph is going to be continuous, then when the number 1 kicks in, when the algebra kicks in at the number 1, it has to have the value 0, which means C needs to be negative a fifth, or else that won't have a value of 0 when you put x equals 1 in. So the algebra I need for the first one is this. Now, this algebra that I built here, when that kicks out at x equals 4, when that kicks out at x equals 4, it needs to have a value of 1. So what does it currently have? That'd be 2 minus, wait on, that'd be 8 minus 4, which is 4 fifths. So if it's going to have a value of 1, then D needs to be 1 fifth. So it's a tenth x squared minus a fifth x plus, what did I say it was? 1 fifth that I need. Okay. Now let's just check if this is going to be continuous. I need to get the same value for when this algebra kicks out at 2 as for when this algebra kicks in. So in other words, if you put the number 2 in there, you should get the same both for this algebra and this algebra. If you put the number 2 in there, you get a fifth. If you put the number 2 in there, you get 4 tenths minus 2 fifths, which is 2 fifths. plus 1/5. So that's not checking out. Let's just check it again. That's 2/5 minus 1/5. That's definitely a fifth. If you put the number 2 in there, you get 4/5 minus 2/5. 4/5 minus 2/5 is definitely 2/5. Oh, okay, sorry. That's 4 tenths minus 4 tenths. So 2/5 is 4 tenths plus 1/5 will be 1/5. So it all checks out. Okay. Now this thing that I mentioned is a very important tool for deciding if something could potentially be a cumulative distribution function. If you catch it decreasing even once, it can't be a cumulative distribution function, as long as it is decreasing in the area where it's supposed to apply. If it doesn't hook up with the number 1 at the end, and if it doesn't hook up with a height of 0 at the start, then it can't be a cumulative distribution function. So just be aware of those things so that you can check that your answers are sensible. Okay, I'll do another conversion now. Let's do a cumulative distribution function, and let's turn it into a PDF. So the algebra applies between 0 and 2. When it kicks out at 2, it has to be 1. When it kicks in at 0, it has to be 0. Okay? Let's build the look. fx is 0 otherwise. The algebra will apply just when the algebra from the CDF did. To get this, you differentiate. So it's a fifth plus 6 over 20x. I just got that by differentiation. Now let's do some little follow-up questions. What's the probability that x is less than or equal to 1.5? Just take the number 1.5 and put it there. 1.5 is between 0 and 2, so that algebra is certainly good. Okay, the whole point of a CDF is that you work out probabilities just by substituting into it. And remember, it only works out to the left of probabilities, but that's exactly what this is. What if they asked you to work out this? Substitute that in. That'll tell you the probability of being less than 0.5. Substitute that in. That'll tell you the probability of being less than 1.5. So the probability of being between 0.5 and 1.5 will be this figure minus this figure. Okay? And finally, what if I asked you what's the probability that x equals 1? That's just automatically 0, because in a continuous distribution, the number 1 is competing with space for billions of other possible values. So no number is low enough to express just how unlikely that it would be exactly 1. Another way of thinking about it is that the area of a probability density function between 1 and 1 is 0, because there's no room to put any area there.